Hi, everyone, and welcome to the first session of the Boyle Winter School on Advanced Secure Computation. And we're very happy to start the school with a series of lectures by Elette Boyle. Elette Boyle is an associate professor and director of the FACT Cryptographic Research Center at IDC Herzliya, which is now known as Reichman University. And she's also a senior scientist at Entity Research. She received her PhD from MIT and did a postdoc at Cornell University and the Technion. Elette's research is mostly in secure multi-party computation, secret sharing, and distributed algorithms. And she received many awards, including the best paper in Crypto 2016. She was an invited speaker at PKC 2018. And she received the Google Research Award and the very prestigious ERC Starting Research Grant. She's one of the founders of function sequence sharing, and we're very happy to have her here and tell us about it. So Elette, thank you for coming, and we are waiting to hear your lecture.
All right, thanks very much, Benny, and thanks to the organizers for putting this on. Certainly with a lot of back and forth with the world, I'm very happy that we're still able to do this. Another thing I should mention, so I've been told there's hundreds of people viewing this. I don't see anybody, which is a little unfortunate. But as Benny mentioned, so if you do have questions, go ahead and on the Slack channel, you can write the questions. And there's a couple students who will pass them along to me. So we'll do kind of checkpoints here and there. All right, so I will be indeed talking about function secret sharing. This is a topic that's dear to my heart. One of the things that really got me going, starting as a postdoc, and has been a big focus of my work. So I'll be talking about sort of a mix of a lot of different results at a survey style. And I have a lot of different co-authors along the way that you'll see, but I do want to put a bit of a shout out here to Niv Gilboa and Yuval Ishai, which for some reason are only them showing. Let's see what we got here. There we go. So Yuval, you'll see in a couple of days. He'll also be talking about related topics. And Niv spoke at the school quite recently, but he won't be this year. So if you see this man, tell him that his research is cool. Okay, so you saw the schedule. A lot of interesting topics at this winter school. Of course, I'm quite biased. But one thing that I want to emphasize here is that actually a lot of these topics have direct connections to what you're going to hear about right here and now, which is this notion of function secret sharing. Okay, so maybe this is sort of your trap. You have to pay attention to this section in order for some of the future stuff to make sense. Okay, so let's start getting into it. What is this function secret sharing? And let me start by introducing something you've probably seen already, which is standard additive secret sharing. Okay, so here in the standard setting, people are waving hands. I don't know if that means anything. We're good. We're good. Good. Okay. So in standard secret sharing, you have some sort of secret element, say some item in an abelian group. Okay. And this is split into two pieces or more, such that each piece itself, each share of the secret hides the secret itself. But there's some sort of additive reconstruction property. Okay, so for standard additive secret sharing, this just means if I add, for example, S0 and S1 together, I get S. Okay, so when we're talking about function secret sharing, it's going to be a similar sort of a flavor of things, okay? You kind of think about now the secret is not just a string, but it's a function, okay? And in some sense, what does that really mean? Well, let's suppose I'm going to use the notation here that our input space is n-bit inputs, okay? And the output of the function is some group element. Okay, so a function itself is some collection now of 2 to the n correlated secrets in G. This is like viewing the truth table here as this mega string, okay? And of course, we can always secret share this giant string in the standard sense. But the goal or sort of the interesting part of this is that if my function has some compressed representation, okay, so instead of giving you a giant truth table, I give you a small circuit or some other type of program representation, is there some way that you can secret share the function in a similar sense, but where the shares themselves are also compact? Okay, so this is the high level. And in our 3-hour, adventure together here, what I want to do is to start in the first hour by giving you more formal, what is the actual definition of this, discussing different properties of this, and a little bit of a highlight of a high-level view of what do we know about this object and what is it connected to. Okay. In the second hour, I'll dive more technically into some of the useful, particularly useful constructions, the lightweight ones. And in the third hour, I'm going to go rogue a little bit and just talk about some random interesting extensions and applications of this topic. Okay, so getting a little bit more formal here. When I say now function secret sharing scheme, okay, this is going to be with respect to some class of functions F. And for this lecture, I'm just going to be focusing on splitting into two parts, into two shares, like the picture had before. But note that you can consider this notion with more than just two shares. Okay, so function secret sharing, or FSS scheme for some class of functions F, has two algorithms. There's some sort of generation, okay? This takes as input our security parameter, this I'm denoting by 1 to the lambda, and F. Okay, so F is this is the secret function that I want to share. And the output of this procedure, gen, is going to be the two different function shares. Okay, so this is the picture that you saw before. And I want to mention that I'm using this notation F0, F1, and I'll use that a lot. And I'll sometimes also interchangeably kind of talk about function keys. So if you see K0, K1, this is playing a similar role, but slightly different notation than F0, F1. Okay, and the second part is this eval algorithm. Okay, so eval takes three inputs. One is the bit saying, am I person number 0 or am I person number 1? Okay, it takes the key. Here I'm already busting out this key notation. Okay, and it takes some input X. And what does this look like? So X, we think of X as some public input that both you and I, so each of us have shares of this function, and we both want to evaluate on X. And given this, each of us without communicating, so each of us locally are doing eval on our own sides, each of us generates some output share, which I'm denoting by Y sub B. Okay, so this is the syntax of an FSS scheme. Again, gen is splitting into two shares, and eval is something that you evaluate on your local share. Okay, and of course, we want this to satisfy some properties. The first, and these two are emulating exactly the two properties that we had of additive secret sharing before. Okay, so the first property is going to be some sort of secrecy or hiding. And what this is saying is that if I just get one of the two keys, okay, so here if I have any pair of functions f and f prime, and I'm just getting one of the two keys, here this is k sub b would be like f sub b, okay, the distribution of that key from one function f is indistinguishable from the distribution of that key if you had instead shared a function f prime. Okay, this is a form of sort of semantic security. You can't tell which of the two it was. Okay, and this definition, or rather, sorry, this indistinguishability can take different flavors as standard. So if this is, for example, statistically close, then this gives some sort of information theoretic hiding. But we can also consider a relaxed computational indistinguishability. That is saying that if we assume some computational hardness assumption holds, then a bounded adversary cannot distinguish between these distributions. Okay, and so this is sort of emulating this security notion. Okay, and of course the last part is the correctness or reconstruction property, and this is saying that for any X that comes along this evaluation input, that if I take y0 and y1 and add them together, this gives me additive reconstruction of the function f applied on the input x. And note that this reconstruction is sort of reusable. Okay, so if I give you, you get f0, I get f1, and we evaluate on one input x, it works. Okay, now some other x comes along, we evaluate it on this x prime, we also get additive correctness. And same for, in fact, any of the x's in the domain. So this is not just a one-shot thing, but you can even expand out if you wanted to for all the possible inputs. Okay, so this is probably a good point for me to pause and see if there's any questions about the definition or before.
So far, there are no questions.
All right, okay. Feel free, the public, if you want questions. Okay, so again, what do we have? So this is the gen algorithm and the eval algorithm. And I defined the secrecy as this form of semantic security. Okay, and it turns out you can consider an alternative notion of security here. So in addition to like an indistinguishability definition, like I just described, you can also consider a simulation form of security. Okay, and this is, so what is this saying? This is going to be simulation with respect to some leakage function L. And roughly what this version of security is going to be is to say that by getting your key f k sub b, you're not learning anything about f beyond some leakage on f as specified by the function L. Okay, and as we know and love in various areas of cryptography, we can define this via simulation by requiring that there exists some simulator algorithm, here denoted sim, okay, such that for any function in your function class, that the distribution of one of the keys, k sub b, is indistinguishable from a simulated version where the simulator only gets to see the leakage L on f and not f itself. Okay, so why consider this, or how do these compare? Well, first of all, actually the simulation-based security notion is a little bit more flexible. It allows you to, based on your choice of L, allow kind of a finer grained hiding versus revealing, okay? And we'll see a couple of examples of that throughout the lecture. And one thing maybe to point out is that in some version of this, or for some choice of leakage function, these definitions are actually equivalent. Okay, and the leakage function that corresponds to that is that if the only thing I'm leaking is what is the function class f that this function came from, okay, and then you can show that these definitions are in fact equivalent. Okay, so this is the definition. Now we've seen what is this object. And let me make a few different remarks here. So as I mentioned, I'm for the purposes of this lecture, aside from one slide at the very end, I'm going to only talk about the case where I'm splitting into two different shares, so just F0, F1. But this is not the only thing that exists. Another thing I want to get you in the mindset for the whole lecture is I'm only going to be talking about so-called semi-honest or passive adversarial setting. And what I mean by that is I'm not going to worry about robustness or that people might give bad shares or that people might actually share the function f improperly. Okay, these are all very interesting questions. And in fact, you'll probably see a lot of this in Henry's talk later on today. But for purposes of this lecture, I'm keeping it simple and just having sort of this passive notion of security, where, for example, given the distribution of one key, I don't learn anything, but I assume that everybody's really acting properly. Another thing, I defined function secret sharing with additive reconstruction. This is in fact the standard notion. There's been, you can consider more general types of reconstruction. Here, I mean, what is the action that you're doing on your output shares with y0 and y1 in order to reconstruct f of x? And we can say different things. We have different upper bounds and lower bounds for more general cases. But I'm going to keep it just additive for my talk as well. And maybe you might be asking yourself, well, why additive? Why is this, why keep it so restrictive? I remember I got this question many, many times when we first came out with this notion. Tal Malkan, if you're in the audience, I remember this. But don't worry, we gave eventually very convincing answers, and I'm not going to tell you what that answer is now, but I will explicitly when we get to some of the applications. Okay, so the short version is that why consider additive? Because we can actually construct things with additive reconstruction, and given additive reconstruction, that opens up a whole region of applications that really does rely on that. Okay, so this now was the definition part, and let's go through and do a couple simple maybe exercises of building a kind of core FSS schemes together. Okay, so the first example, in fact, I already slipped a few slides back. So one possible construction of FSS for the class of all functions, okay? And how can you do that? Well, remember I said, if you take the truth table of your function, you could just view this as some giant string, okay? It's a lot of different symbols in it. And just go ahead and secret this giant string symbol by symbol. So how does homomorphic evaluation go? Kind of putting it in the framework. So if some public input X comes along, how do you evaluate your shares here? I'm pausing so that you guys think about it. Okay, the answer is that given your giant truth table, you'll look in the position that corresponds to that input X. And whatever's written in those positions becomes your output share. Okay, and exactly by the construction of this scheme, where we're truly just additively secret shared each output symbol by symbol, these two things add exactly to what's written in F here in the X position, which is F of X. Okay, so this is kind of a naive, default construction that holds no matter what your structure of your function class is. Okay, of course, the downside is that this is not particularly efficient. So in particular, the share size here is scaling with the entire truth table of the function. And reminding here, so here I'm maintaining the notation that the input to our functions is going to be n-bit strings. So here 2 to the n, this is exponential in the input size. Okay, let's take another step forward. Suppose that the class of functions that we want to share are linear functions over some ring R. Okay, so each function f of x is of the form ax plus b, where a and b are two secret ring elements. Okay, so on pause again to see if you guys have any thoughts. How can we secret share such a function? And note, by the way, so what does the truth table of this function look like? Well, for every single value of x in the ring, I have some output. So for example, if the ring is very large, then the truth table of this function would also be very large, which is undesirable. Okay, but we don't need to use the whole truth table for such a function class. Okay, for example, suppose that you just take the coefficients a and b, and you additively share them over the ring R. Okay, so that is a0 plus a1 is equal to a, and so forth. Now, how do you evaluate these shares? What does this give you? Okay, so suppose that some public x comes along, and the action that I want you to do is to take your shares, for example, a0 and b0. These things on their own are totally garbage random ring elements, okay? But I'm going to pretend as if they are the coefficients, okay? And I'm going to evaluate exactly a0 times x plus b0. And the second party does the analogous. Why does this give us additive secret reconstruction? Okay, what happens when you add these things together? Well, if I first add here and then I add the two, that's the same thing as adding up and down first. Okay, so first adding these two and adding these two and then adding together. And remember, a0 plus a1 is equal to a, the secret coefficient. And by linearity, I have that a0 times x plus a1 times x is equal to a times x. Okay, so this exactly gives you the reconstruction that you want. By the way, why is this scheme secure? Why is it private? Why are we hiding? Okay, well, if I only get additive secret shares of the coefficients, this actually gives me zero information about the choice of the real coefficients themselves. Okay, taking another step up here, slightly more general. Suppose that I'm looking at the class of polynomials. Okay, so here not just ax plus b, but I've got ax squared plus bx plus c, for example. Okay, you can consider more general degrees of polynomials. What are we going to do now? Any thoughts on this? Okay, well, maybe the fact that the first one was a linear function. Linear certainly seems amenable to these kinds of evaluating on secret shares. But it turns out, actually, essentially the same construction will work. Okay, so here, for example, additively secret share the 3 coefficients that you have. Now, how do you do evaluation? Well, remember that x is public. So, for example, x squared is also something that both of us can publicly compute, okay? And now we can exactly do the same thing that we had before, where for each monomial here, we're going to multiply it by our share of the corresponding coefficient. Okay, and in the exact same way, this will add together exactly to the polynomial evaluated on our x. Okay, and if you guys are looking at this, maybe you're observing here an interesting observation, which is that this general framework has actually nothing to do with the fact that x and x squared or x cubed or whatever are polynomials. This general approach says that if I have any secret linear combination, here the secret linear combination corresponds to the secret coefficients a, b, and c of any collection of public functions of x. In this case, it happens to be x squared, x, and 1, okay? But you can have any function that you want. Then that class of functions can be function secret shared exactly in the same manner, where you just secret share the coefficients of the linear combination. Okay, and so keep in mind these sorts of tricks come in handy, especially when we're trying to construct more complex function classes. That these sorts of maneuvers will be useful to keep in mind. Okay, and one kind of final takeaway of this, also observe that this is in fact using even a more basic observation here. So suppose I have a function secret sharing scheme for some function class f, and I also have one on the side, maybe it looks totally different, for the class g. How can you get a function secret sharing scheme for a new class that is sort of the sum of these two things? Here I'm defining the class capital F plus capital G as the collection of all the functions f plus g, where f is coming from f and g is coming from g. Okay, and in fact, it's going to line up exactly here in this picture. You can do this by, take your secret function now f plus g, run the first secret sharing scheme for f, that's the blue here, run the second function secret sharing scheme for g, and now give you just these 2 shares, one of each kind. And however these evaluation procedures were up here, you'll do that for each of your shares, okay? That yields some output share for the first scheme and also for the second scheme. And you simply add those output shares together as your output share for this f plus g. Okay, so now we've covered another collection of constructions, or I'll pause it and see if there's any questions.
Yes, there's one question. Amit asked if for the truth table FSS construction, semantic security is the same as simulation security.
Yes, and well, okay. In fact, the scheme is so secure that it's sort of perfectly secure. So both of these will be satisfied. In fact, so jumping back to the definitions, when I'm doing in fact, all of these constructions that you've seen so far are information theoretically secure. and even perfectly secure. So in the sense that your key distribution is identical, no matter what the original secret function was. So for example, if I'm giving you additive secret shares of the truth table, this is giving you zero information, even information theoretically. If you were completely all powerful, if I give you 1/2 of an additive secret sharing of the truth table, this is truly just a bunch of random garbage. It is giving you zero information about what the original function was. And so in particular, these two definitions of semantic versus simulation-based security sort of collapse. They're the same thing. Any other questions? Okay. Okay, so as I mentioned, all of the constructions that you've seen so far are information theoretically secure, in the sense that even if one of the two parties is completely all-powerful computation-wise, you still have security. Okay, so these are, on one hand, information theoretic security is fantastic. It's a very strong notion. We love it when you can get this. But it turns out that this function secret sharing as a class is a little bit limited as to what you can do information theoretically. Okay, so now I want to pivot a little bit and start talking about types of classes of functions where, in fact, you can only hope to get this with computational security. And one such really central and useful example is function secret sharing for the class of point functions. Okay, so a point function, here I'm denoting this by either f sub alpha comma beta, or sometimes I will omit the beta and just write f sub alpha. Okay, this is the class of functions from n-bit inputs to some output group, such that the output is zero almost all the time. Okay, the only non-zero output is if you exactly input the special value alpha. Okay, so in general, if you input alpha, you get beta. If you input anything else, you get zero. Okay, so first of all, this certainly is a very different beast. And in fact, for example, we were using a lot of nice homomorphic properties of sort of structures or simple notions of these linear combinations of public functions. And now, for example, suppose that you were to evaluate your share. So suppose that I gave you this FSS for point functions, which, by the way, is so important. It has its own name. This is known as a distributed point function. Okay, it's exactly the same thing as FSS for point functions. And if you were to evaluate your share, okay, on every single input in the domain, what does that mean? So I get a bunch of zeros and ones here, for example. The other share will also get a bunch of zeros and ones. And if I add these together, I know that I get the truth table of a point function, which means if we're doing arithmetic over Z2, that almost all of these points agree, and there's just one special location at location alpha where my two values disagree. Okay, so this is here when I'm considering the output space being Z2, and the special output is 1. And note here, so I want to point out something. I've sort of drawn out the whole truth table here, but note that the shares, my F0 and my F1, are going to actually be much shorter than the truth table. So in some sense, you can view function secret sharing as a way of compressing additive secret shares of the truth table of a function. That's exactly what it is. Okay. So this class of functions is a very different beast. Turns out it's very useful, as I said. And in part 2 of today's lecture, we're going to go through and actually give a construction of how can you get a distributed point function. Okay, so this is closing up kind of some simple playing around with initial constructions. And what's up for the remainder of this hour? I've got 2 different things. I want to give you a flavor of why these are useful, this FSS, especially FSS for point functions. And this will be a simple application setting relating to private data manipulation. I'll explain what I mean there. And I want to close up this section by talking about a little bit at a high level. What do we know about constructions of FSS? What do we know exists? What do we still not know? Okay, so going toward this sample application, the setting is going to be the following. Okay, suppose I want to make private queries to some public database. And for example, I can consider different settings where the database is either held just in a single server, or suppose, for example, it's held by a collection of different servers that are non-colluding with each other. Okay, so I'm a client. I'll generate some message, some query that goes to possibly all of these different servers and get information back. And my goal is to give some query and to be able to learn that query evaluated on the database. Okay, but while hiding what was my query to the servers. Okay, you could think about, for example, maybe I'm querying stock quotes. Okay, the quotes themselves, this is public information, but which ones I'm interested in is something that I might want to hide. Or for example, a map search. Again, maps, the map itself is not sensitive data, but for example, where I'm trying to find directions to is something that could be private. Okay, and note that here in this setting that the client doesn't own the database. So for example, this is, I'm using the same map that you're using, that everybody else in the world is trying to query. So this is not something that, for example, I could just pre-process the data as it's going. Okay, and those of you who have heard of private information retrieval might notice that this looks very familiar. Okay, so one example or one specific case of such a setting is where the private query I'm trying to make is just tell me what is the ith item in this database. Okay, so this is, say, labeled from 1 to some length of the database, and I want to retrieve index item I, but while hiding the index from the servers. Okay, so private information retrieval itself is a whole topic. In fact, Dima is going to be talking about it as a whole topic in this winter school. But I want to give a little bit of first of all, high level of what do we know about this thing, and then coming back to where does function secret sharing come into play. Okay, so suppose that my database has n entries, each is 1 bit. I'm a theoretician, let's say. So it's possible for getting statistical privacy, even if the servers are all powerful. This for 2 and more servers is actually a really interesting line of work that lies a little bit outside of cryptography. It has to do with locally decodable codes and things beyond this. It turns out you can get the communication. So here, what I've written in these numbers here is referring to how much communication do you have to send, how many bits do you have to send back and forth with the servers. So this is slightly kind of n to the little o of 1, slightly less than any polynomial n to the epsilon. These actually are quite relatively complicated constructions. If I want to do this with just a single server, with statistical privacy, it's impossible. Okay, it turns out actually, even as soon as my communication is 1 bit less than the entire database, just downloading the entire thing to get privacy, that this already requires public key cryptography, something known as oblivious transfer. Okay, so if you relax to computational privacy, this is where, in some sense, the efficient private information retrieval schemes exist. And here I'm going to go back to denoting lambda as a security parameter. With 1 server, you can do it with sort of the communication that you'd want. But the types of operations are inherently, as we saw, inherently public key. And in particular, they rely on structured public key encryption assumptions. On the other hand, so I'd like to argue that this is a bit of a sweet spot in this grid. If you just want to assume one-way functions, kind of the lowest amount that anybody really assumes in cryptography, and you have, say, 2 servers, so that there is a trust assumption there that there's 2 servers who are not communicating with each other, all of a sudden, the constructions became really efficient. Okay, and this lambda plus 2 log n this is something that you're going to see as a corollary of things that we're going to build today. Okay, so this is the setting, kind of just copying over here. So this is the setting of two non-colluding servers and allowing you to use lightweight cryptography. So here, one-way functions, what do I mean? Well, concretely, for example, if you assume AS is something that's not broken, this is already enough to get you moving. So this is lightweight symmetric key cryptography. Okay, in regard to the non-collusion assumption, it's a good question, but there are a lot of practical settings where this is realistic. So for example, if you have different providers or different subpoena jurisdictions, kind of bringing the law into it in combination. Okay, and as I mentioned, for all of this, which extends also to the private information retrieval setting, I'm just considering a passive adversary. So I'm not dealing with servers trying to cheat or anything like that. Okay, so the punchline here is that FSS for point functions, remember this is distributed point functions, implies to server private information retrieval. Okay, so what is the construction? Suppose I, the lovely client, am interested in accessing item I. Okay, think about a point function, okay, whose input is n items. Sorry, here my notation is slightly different. This should maybe be capital N. So here this is the set from 1 to n, whose output is a bit over Z2. Okay, this is what that point function is. And consider using the function secret sharing scheme to split my point function. Note that this is private, okay? This is my private point function because it has my desired index I. Okay, split it into two different pieces and send one share to each of the servers. Okay, the servers take this function and essentially expand it out, okay, to this the secret sharing of the truth table. So this is exactly what's being lined up here. So this is kind of, I was drawing this horizontally before. Now you can think about this vertically. This is evaluating its share on every single input of the domain and using this as a coefficient, okay, to take a subset sum of the actual data items. Okay, so what does this mean? So for example, this server here, in each position where there's a 1, it will take that data item and include that, pile that into a giant sum. Wherever there's a 0, it will not include it. Okay, and same for this server down here. And so this yields something compressed down. This is this y sub a, for example, or y sub b down the bottom. This notation means it's the sum, and the sum is over, say these are bit strings, okay? Value of j is like the value, the payload that's written in each index position j, and f sub a of j is whatever the corresponding coefficient is. This is the evaluation of my function share at index j. Okay, so collapse down each of these things and send back now a single value. Okay, and observe here that y sub a is exactly the size of one data item in the database. And yeah, if I was in front of everybody, I'd make you guys solve this actually. Where do you go from there? How do you finish this protocol? Okay, well, the client, myself in this case, takes the two values that were sent back from the servers and simply adds them up. Okay, now what is the answer? What does this give us? Well, let's think about it entry by entry in the database. If I'm an entry that's not in position I, then the coefficients here are a secret sharing of 0. Okay, either they're both 1 or they're both 0 because we're over Z2. So what that means is that the two servers are either both going to add the value in which case it cancels out, or neither will add the value in which case it's not there in any case. The only position that has a secret sharing of 1 is exactly the desired position I. Okay, so this is going to be the one value that's pulled out, and the rest will all cancel out. Okay, so this gives you a correctness. Why does privacy hold? Why is this actually a private information retrieval scheme? Well, take in consideration. So what is the information that each server saw is a single share of my, my distributed point function, either FA or FB, which exactly by the hiding property, the secrecy property of the function secret sharing scheme, hides what my function was. In particular, hides the index I. Okay, so this is a two-server peer scheme. And what's very cool about this is the communication. Okay, so what is communicated? For example, to each server, I'm sending one function share and getting in return something that's exactly the size of one value in the database. And plugging in constructions of how tight, how efficient can we get FSS 4-point functions, this is going to work out to be roughly logarithmic in the database size. Okay, so this is FSS implying two-server peer. And let me say a few words about extensions beyond this. Okay, so this is like the base kind of application of this private database manipulation. This is just a private information retrieval. But beyond reads, for example, in a sort of dual setting, you can use function secret sharing for private updates to secret shared data. Okay, so here it's a different setting. I no longer have identical copies of a database. That's what you need for private reads. Okay, for private writes, I want to think about the servers as sharing a secret shared version of a database. Okay, so each one on its own just looks like garbage. And for example, suppose I'm doing an application of histograms. So I want to keep some count of, for example, how many votes does each candidate have from 1 to n? So I come as a client, I want to increment position I, say by a 1 value. In a very similar way, I'll define a point function that's non-zero exactly at input I, secret share this, okay? I send over the shares. So far, this is identical to the private information retrieval setting. Okay, but now how these shares are used are going to be a little bit different. So again, the servers will evaluate this, sort of expand it to the entire secret shared truth table of this point function. But instead of using these as coefficients for scaling and collapsing something down, in fact, I'm not even expecting to get anything back again, right? I just want to increment the position. I don't need any message back. I'd go on with my life, okay? So how is this executed? In each position here, this value is incremented by whatever this value was here, okay? And actually, so this is actually a typo. I should fix this. Note that this is a different sort of output space because you want this output space to be over some larger thing. So not just 0, 1 flipping, but for example, over some larger Zn, where you know, say capital N or a Zm, where M is going to be a bigger than or equal to the total number of votes that you're expecting for anything to apply. Okay, so this arithmetic structure is a little bit different. But note here, one of the cool benefits about this scheme is that anybody can increment. I don't need to share any secrets with the server. I don't need to share any secrets with you. I don't even need to trust you. Okay, well, you'll see in Henry's talk how you can make it so that you don't even need to trust. Okay, but anybody can do this. Okay, this is even beyond simple functions like increment index I. Okay, so far you've seen private information retrieval, which was retrieve index I, and private histograms, which was increment index I. But if you have FSS for different types of point functions, or as we'll see, even different classes of functions, you can increment or you can retrieve in more sophisticated types of queries. Okay, so for example, suppose that I don't just want to increment index I want to increment every index that satisfies some property. Okay, and maybe this is even a function of public information. Say it's a list of, say I have a list of candidates, right? Or I have a list of candidates and information about them, and I want to increment the vote count, the histogram count for every candidate such that their information satisfies some predicate. Okay, if you have, so here this is beyond point functions, but if you have FSS for this class of predicates, okay, then you can actually do exactly the same sort of construction here, and you'll just have a slightly different truth table. This will be essentially a secret sharing of a different kind of truth table. Okay. And so just to mention here, now that we're going beyond point functions, I want to emphasize, so what is sort of the leakage? What are you revealing to the servers? Okay, so it's not nothing, right? In fact, with the point functions, I revealed, or you already sort of knew, that the types of queries I was going to be making was just what is the index, or what is the value at a specific index. Okay, and more broadly, so if I have FSS for some broader type of predicate class, then I'm going to I could potentially reveal what is this predicate class, right? Because you know you're getting function secret shares from some class. Like you have to know exactly how to evaluate these, for example, and that evaluation is already tied to some function class. Okay, so now we are ready to finally answer at least a couple of the questions here. And the first question, remember I asked before, why additive reconstruction? Okay, when we're considering function secret sharing, what is the benefit or what is the use? Why bother restricting this to being additive reconstruction? Okay, and this application class, this whole category of private reads and private writes, exactly uses the fact that the reconstruction is a linear function of the secret shares. Okay, and roughly why is that? In some sense, it's because the reconstruction function commutes with these additions that you're doing. For example, for private information retrieval, the additions you're doing to compress down and have the server be able to send a short message back. Or for the private writes, this operation that they're adding in the shares locally to a given position. You're adding this share, you're adding the share from some other client and so forth. And that commutes with the fact that whatever I'm doing and whatever you're doing have some sort of effect together. Okay, in fact, even to the extreme. So if you did, for example, if your reconstruction was like an and or an or, you can actually prove lower bounds about what would be the communication complexity if I'm using such a function secret sharing scheme for trying to get private information retrieval. It's kind of an interesting connection to communication complexity. Another question, perhaps maybe some of you might be asking yourselves. So the construction that I gave for private information retrieval, for example, requires that the servers do linear amount of work in the database. Okay, so for every single item in the database, they had to do some, not only this linear combination, but also they had to evaluate the FSS scheme on each and every item. Okay, certainly, so those who have seen private information retrieval, unfortunately, this is sort of inherent. Okay, but let me even go further and say, even if we didn't need to do linear computation, okay, and remind when you guys see Gilad's talk about oblivious RAM, keep this in mind, because there are similar, and I'm not going to describe exactly what this is, but both private information retrieval and oblivious RAM are ways of trying to do a retrieval of data items in a way that hide which data items you're accessing. It's a little bit of a different setting, Gilad will describe. Okay, and oblivious RAM allows you to do pre-processing beforehand, and the client owns the data and everything. And because of that, you can get much lower server complexity work. For example, logarithmic. For each access, the server only has to look at log positions, okay? So if you were comparing these two things together, you might think, my goodness, why would I ever want private information retrieval, which needs linear work in the database size, versus oblivious RAM, which only needs log size? And let me say for now, sometimes this is not so bad. And in fact, there's a specific work due to Donner and Shalat that showed somewhat surprisingly that this can actually be much more efficient in certain cases. For example, if you're doing secure computation of some computation where you need to hide which data accesses you're doing. Okay, and the final comment here, which I already sort of addressed. So what is the leakage during these things? Again, what you are revealing is the query class. Okay, so I have FSS for some class F, and the servers will know I'm asking some query from this class, but it hides which is the actual query from within this class. Okay, so this is good motivation for us to try to get FSS for bigger classes of functions. For example, this allows more correctness and also more hiding. Okay, and just kind of pushing this point forward a little bit more. So if you do have FSS for more general function classes, this gives you more expressive database manipulations. I showed you, for example, voting secret histograms for private updates to secret shared data. An interesting sort of surprising application of the same framework is anonymous broadcast. This was shown by work actually of Henry and others. For example, attribute-based information retrieval, say like multi-keyword search or range queries or database statistics. Okay, these are all sorts of things that you can do with this machinery. Okay, and just as one maybe kind of more concrete example, so suppose that there's some database here of items. This is something now I'm doing a private retrieval. So both the servers have identical copies of this database. If you can kind of see here, so this database has different entries. It's got name, it's got salary, date of birth, and gender. And suppose, for example, I want to do a counting query. How many people in this database have salary within some range, and their birthday is in October, and they are female? This is the sort of query that you can potentially do privately using function secret sharing. Okay, and just to kind of give an idea here, so this will be for some sort of more expressive predicate class F, okay, which is evaluating to 1 if these things hold, okay, and 0 otherwise. And now, how do you do this? So suppose I can secret share this specific secret predicate, okay? Now, keep in mind that you can apply the predicate, so the predicate doesn't need to just be evaluated on the index, which was what was in the special case of private information retrieval, but the predicate can be evaluated on any public input information. So by public, I just mean basically anything that both of the servers know. For example, I'm evaluating this on values of the salary. Is it the case that, for a given row, is it the case that this salary is in whatever secret interesting range I'm interested in? And this date of birth satisfies that it's in October, and this gender is a particular value. If it satisfies all of that, this FSS will increment a count, or rather, this will evaluate to 1 or 0. And if you add all of them up, if you do this instead of over Z2, which gave you just flipped, do I have an odd or an even number? If this arithmetic is instead over a larger class Zn, then these values actually add. 1 plus 1 is equal to 2 and not 0. Okay, so this is a way, for example, that you can do these types of counting queries. Okay, I'm coming to the end of this part of the lecture. Actually, let me stop very briefly and see if there's any questions about this application setting.
Yes, we actually do. We have quite a few questions, so we'll stick to 3 high-level ones.
Okay, sounds good.
So the first is, can we see garbled circuits as a weak case of function secret sharing?
Interesting. So you can consider garbled circuits as a form, but the reconstruction is not going to be additive. So yes, you can do. Actually, I was thinking about putting slides in this as well as sort of playing around with weaker notions. So short version is yes, but the reconstruction is not additive. And unfortunately, for example, that means that these types of applications won't go through directly.
Thanks. So the second question is with regards.
Actually, maybe sorry, just one clarification point there for those in case it's unclear. So what are the function shares? One, for example, one of the 2 shares would be a garbled version of your function, and the other share would be like the input labels, like the set of all the input labels, if you know what that means.
Great. So you also discussed an application to private updates to secret shared data.
Yes.
The question is it possible to privately write and read the database at the same time?
Interesting. No is the short version. Not if you, okay, so in order to, if you only have 2 servers, then for reads, you need the servers to hold identical values. And for writes, you want them, or they will over time be holding secret shared values. So it's a good question. If you want to be able to do both, then, for example, if you're able to increase your assumption of how many servers you have, say, for example, if you had 4 servers and only one of them is corrupted, then you can kind of put the 2 together.
Great. And our final question for this session will be, so I suppose that point functions cannot be described as a low-degree polynomial. So
Correct.
If you have FSS for the class of low-degree polynomials and for point functions, is there anything useful you can do here?
Well, the good question, because we indeed do have FSS for low-degree polynomials, and we have FSS for point functions. And let me kind of actually use that as an excuse to keep moving, because I want to say, what is it that we do have FSS for? And I see that I'm running a bit over time, so let me cut this a little bit brief. Don't worry, I'm almost there. Just a very brief aside. So if you've ever heard of homomorphic secret sharing, perchance, note that this is highly related to function secret sharing. It's essentially the dual notion. So here with function secret sharing, we're saying I have a function that I'm secret sharing, and the input is what we're evaluating. And in homomorphic secret sharing, it's flipped. So my input is what I'm secret sharing, and I have some function or program that I'm homomorphically evaluating. Note that FSS for a program class P is not exactly the same thing as HSS for program class P is not exactly the same thing as FSS for program class P, but they're clearly strongly related for certain program classes. Okay, I'm doing this first of all because both of them they're very tightly connected, but one versus the other can be more natural in different applications. And this is because actually what I'm going to write on this slide is a little bit more natural to describe in the setting of homomorphic secret sharing. So I'm cheating a little bit. But for each case, how do you translate this to the corresponding function secret sharing class of programs? It's essentially the dual. Okay, so this slide is going to describe what are the constructions that we know. Okay, we saw already down at the bottom without any computational assumptions. So the red is the computational assumptions. The green is what is the class. We know how to do linear combinations with secret coefficients. Okay, at the very, very high end, you can get all circuits if you're willing to assume basically, circular secure FHE or some sort of LWE plus. This I would not put as efficient. It in fact builds on top of specific FHE. But bouncing, so here down in this low level, in fact, this is the category we're mostly going to be focusing on today. I'll say more about simple functions, in fact, in the next slide. But these are going to be lightweight, and these will be based on one-way functions. As it turns out, as soon as you, even for these simple function classes, you already need one-way functions, so you cannot achieve these information theoretically. And bouncing up higher, so you will not see any of this today, but there are these mid-level constructions that handle branching programs. You can think about this around the level of NC1 or log depth computations. And there's been some exciting activity in this area actually in the last year based on Polynomials. But each of these things, so if you don't know what this means, DDH, LWE, Polynomials, doesn't really matter. Each of these are specific structured assumptions that are public key assumptions. So each of them imply public key encryption. And there's this odd, sort of incomparable, the LPN and the one-way functions, depending on which constructions you're looking at. But we have ways of doing low-degree polynomials. So note here, this is not low-degree polynomials in the sense that I described, where it was just the okay, it's like now you actually need to take your secret thing and put it to some degree. This is an artifact of the HSS versus FSS. Okay, so this, never mind, but just think about this as this is a slightly more rich class of things that allows you to multiply. And also what I'm going to write as weird PRGs, I'm not going to explain what I mean. Perhaps Peter or Yuval will when they talk about pseudorandom correlation generators. Okay, so this is sort of the lay of the land. I had this picture of, you know, of the sky and the mountain and the valley. At some point there were like two, there was high level and low level, and then there was 3 levels. And so I had this, you know, 3-part picture, and now there's all these additional levels. But really interesting constructions. And what's very interesting, I think, is that in each of these categories, it uses totally different techniques and different mathematical structures. Okay, so today, though, I'm just going to be focusing on this low-level category here and zooming in a bit more on that. So this is based on one-way functions, more specifically based on any pseudorandom generator. There's like for example, length doubling pseudorandom generator. And the main categories are point functions, which we talked about, interval functions, where you're equal to 1 just in some secret interval. So as point functions allows you to do things like private information retrieval, retrieving a specific index, or keyword search, retrieving something that a string matches a specific secret string. Interval functions allow you to do things like range queries. And there's a bit beyond it that we can do. So for example, small constant dimension intervals, which allows you to do a small number of conjunctions and simple decision trees. These ones I'll talk briefly about, but the main part of next section is going to be building point functions and interval functions. Okay, and with this, I will close up the first part where the cliffhanger is, okay, oh my goodness, I really, really want this thing. How do we actually achieve it? Okay, so I believe we have a 15-minute break.
Okay, thank you, Elette. Yeah, we do have a 15-minute break. I'll just tell Elette, because she doesn't see the audience, we have more than 200 people watching you live. So that's great.
Wow.
And more, even though it's an early hour and weekend, it's really impressive. And to the audience, we know that the resolution is not good, and we'll try to fix this over the break. And now it's time for the break. See you soon.